must be the DRL crowd. Okay, welcome everyone. Could you please be quiet? Okay, it's been a long afternoon for you, and we're going to be as brief and precise as we can to let you out of this room and to enjoy the drinks and social meeting. I am Michael Weinstock. I'm one of the directors of the founding director of Emergent Technologies and Design program, and these are my colleagues who I'm going to ask to say a little bit about themselves. George Dronamides, Evan Greenberg, and Manya DeWalt. George?
Well, good afternoon. As Mike said, it's been a long day. I've been working at the MTech for about 10 years, one way or the other. I'm not an architect. My background is in engineering and material systems. And I certainly found a big challenge to interact with the architectural community. And there are lots of synergies that we are hoping to develop within the MTech program. It covers systems, materials, urban scale, biology, but all that is really designed to give you a little bit more thinking processes and open up a little bit more your horizons, because you never know in this life what may be the germ of an idea and something which will lead you to a successful outcome. So I will be meeting you in the next months, okay? And good luck for a good start. Thank you.
Hi, I'm Evan Greenberg. I'm the studio master in MTech. I studied in MTech 2007, 2008, and I've been teaching in the program for 6 years now. I also teach in technical studies in the undergraduate school, so I'm kind of here more or less all the time. I've worked in the US for architects, engineers, and artists, and I've worked in London for both Plasma Studio and Populous. And say my interests in general, I have many, but really interested in kind of exploring the embedded intelligence in material systems, natural systems, fabrication systems, and urban microclimates. And you'll see a lot of me, so I'll stop talking now.
Hi, I'm Manja van der Worp. I'm also an MTech graduate from 2007, so the year before Evan. And it's my first year this year to join this group, which is amazing. I am an architect and a structural engineer, and interested in how we can relate, let's say, structural behavior to geometry, fabrication, and really understanding how we can grasp all these kind of plane parameters and embed it into the interesting systems that you're going to develop. So that's it.
Okay. No, that's fine. That's fine. Good. She's very enthusiastic. And we are extremely pleased that she's joining us. Actually, she's worked with us for a long time. George is the founding, the master, and the first ever chair of biomimetics. So MTech is founded on a kind of biological paradigm. Both of us are lifelong students of biology. For myself, it's genetics and the structure of the genome and kind of biological computation, which I'll show in a little bit. And for George, it's how the material properties and material organization of biological materials produce strength. For both of us, we take these knowledges and show and explore with you how they can be applied to architecture at a variety of scales. We're the core team. We're joined by many other people. We also have a list of masterclasses. This will be extended, but we normally have somewhere between 7 and 8. We have a number of workshops, so we have a high number of people who come in for between 2 days and a week to help with the teaching. For example, we have a graduate from last year who's developed a new plugin for Rhino with Barahapo's Smart Group, and he's going to come in and teach how to use it. I think it's publicly available next week. Okay. So this is how we're organized. More or less like DRL and the other programs, We have a talk part and a dissertation part, which is your research and what you do for either MSc or MArch dissertations. We also do a design and build, but we start here with what we call a boot camp. It's a 3-week induction course. It's pretty intense. So everybody, no matter what your experience, you go back to the beginning. Some of you maybe used to be working in teams, but you're producing a material system. And within those 3 weeks, there are a number of lectures and seminars and software tutorials, and that helps us set the environment and structure for the first term. A few slides of some of the things the students have produced in the past. You're familiar with all these kinds of things. We're particularly keen on how we describe and model and draw behavior and variations. And you'll see some of these. You'll also see many of these ideas that students develop in boot camp in a very quick way, later on get further enhanced and developed. This is one that started in boot camp. It becomes this is a full-scale piece that is tested. They're really arms that collect water, and as the water collects in them, the accumulated weight works with the fiber orientation of the wood to change the curvature and to drop it. And we have different ways of kind of studying this. All of these things we try to teach you. You will become very familiar with analytical software. We have our own way of teaching it. We've been doing it for many years, and it arises in Biomimetics, which I'll show in a moment, and maybe ask Evan to talk about. We work with multiple cycles of physical testing, digital variations, analytical software to see how the behavior, does it correspond between analytical models and physical models, and what are the differences. And these are accumulated and produced into fairly straightforward designs for Course Studio 1. We don't have a set structural paradigm. We explore lots of different structural methods. This again is early model from Core 1 of the 10 secretary system, which has its kind of digital further explorations. And you will see many of the variants that we produce. We teach a little bit of scripting, but you learn very rapidly, and most people become quite quickly expert on that, how to proliferate, but how to produce variations, measure them, see how they behave, and we don't use the word optimize, but how you can choose in a family of designs a particular one that's approached. This is physical modeling. The correspondence between, this is the rapid prototype model, which we show a little bit of, and you have specialized courses and master classes dealing with that, and analytical softwares. But these kind of techniques arise, and we teach them in the Biomimetics course.
So just to give you some more examples of the kinds of things we begin to look at. But really, I mean, you see a lot of these kind of colorful images, and this is kind of, I think, to entice you, to get you excited. But the Biomimetics course is much more than just producing some nice images. So George delivers a series of lecture courses, and then that kind of culminates within kind of an intense workshop environment where we investigate natural systems and kind of look at 3 different areas in a way. So the first is research. So we develop a method and a framework as to how to look at natural systems and extract the organizational principles, mathematical and geometric logics, etc. Then we have kind of an analysis period. So this is what you see on the screen, where we begin to look at how to think analytically, but we also begin to look at how do you use the tools in order to simulate and to analyze. So we use structural analysis software, we use computational fluid dynamics software, and this is all ways for us to build skills, but also to begin to understand how to read systems and develop our own ideas of how we can develop these further. So the Biomimetics course doesn't aim to kind of develop a design at the end, but really develop a system. So how do we think through systems? How do we think about material properties and how they can translate, how the logic can scale even if the material doesn't, etc. Just flip through a few more. So you can see we start from a Venus flytrap and it really ends in this kind of double-layered pneumatic system. So we try to leave the biology behind as fast as we can. Another example, this looks absolutely nothing like the Mimosa pudica, but it operates in a similar logic. So we study both the morphological model as well as the, let's say, the mathematical model, and try to begin to compare the two so we can begin to develop architectural systems. Some examples of the tortoiseshell from last year, and that's it.
So just to emphasize that point, fluency in computational systems is not an end in itself, but in MTech, you will become fluent in these things, but you also learn how to use them and apply them in a way we make no distinction between architecture and engineering. So we don't have kind of designs that someone else will work out and so forth. So many of our students end up, if they're architects, many of them end working in the specialist groups in many of the London practices or in engineering offices. You will become confident. We also every year do a construction project. This is not assessed formally. There are some survivors of it here. It's still ongoing. This is what they did this year. I think it's a heroic effort. It's one of the most complex we've done. It's in the Arup Foundation. Evan is going to show it to you tomorrow at?
Meet me at 4:30 outside of 39.
Okay, so number 39, just along there. If you're on the pavement at 4:30, he'll walk you over and you'll see it. And if you stay till 6, you'll see these guys taking this apart. It's going in a truck, and there's Jose, and it's going to the Timber Expo in Birmingham. So, and you'll get a presentation on this later in the course. Next few slides are from the Emergence course, but the important principle I want to make is you work in a group, but you design in families. You don't design the singular, refined, optimized object, because any optimization is only as good as one set of parameters. So we start like this with families of designs, and you in control of the 4 or 5 parameters that control its morphogenesis and its behavior. And there's this, a few years ago, I was the very first to develop a way of spatial consequence of genetic structure. And you can see each one of those has its little genome. It exists within a family. This is the actual logic of how the spatial volumes are moved around, how they begin to aggregate according to program, and the finished family set of that. Okay. The last year and this year, you'll be applying these kind of logics to the evolution of the urban block. And we do a little history of it. There's a couple of guys smiling there who recognize what it is. It's the highest density that we know has ever been achieved in an urban block. And I was very lucky to see that as a child, although it frightened the life out of me at the time. It doesn't exist anymore. This will be part of our analysis and lectures at the beginning of Core 2, City of Darkness. We also look, sometimes not with great favor, but we look at the current practice of urban blocks and their engineering and climatic formations. We look at various different ways of modeling them. The typical description, this is not an MTech image, typical descriptions that are made for developers and planning authorities. We try to look critically at that. And what we try to do is use these kind of logics and embed them in simple scripts and growth models to distribute across sites. Of course, this is all quite experimental, and we can do this very rapidly. You're pretty much expert at this kind of thing within a few weeks. The questions that arise then is, how do you evaluate it, and by what criteria? Every year, the groups in Core 2 produce a high-density design, 100,000 people plus on a piece of a London site. By then, you're quite familiar with these things, and we have quite strict parameters of what you can achieve. And you'll get a small presentation of some of the projects from last year on this. Okay. We also have been building up for a number of years, as good biologists might do, tissue samples of cities. Some contemporary and some very ancient, but in all of them we're looking at the relationship of these kind of parameters, which are fairly conventional in urbanism, with cultural behaviors and cultural spatial logics, which are inherited and can't be defined by you or me. And we have a lot of different kind of computational models, which we've been fairly successful with. We have modes of analysis that run iteratively with those generative systems. We're able also to relate those to various kind of flow systems for rising sea level and so forth. We work across all kinds of softwares and all kinds of physical modeling. What we try and teach is not just how to use the software. I think anyone can do that. I'm maybe a little slower than Evan is, but pretty much we can all master the software if someone shows us how to do it. What we try to teach is the computational logic behind that. So someone of my age and George's age have seen 5 successive kind of software revolutions. What stays consistent over all those multiple years is a computational way of thinking. So we start very simply always to diagram those, find ways to do that. Once you have these kind of concepts, you can very rapidly develop your kind of scripts and codes in modules and move things around. But we also need to know, well, if we can do that, how do we know it's any good? It can look really nice. You can make amazing renders. You've seen a lot in the past. You see them online, see them on Facebook. I think even in our Facebook, we have 1 or 2 renders, but generally we don't do renders, or we try not to do many. What we try to do is measure, quantify, analyze, and then we return those as inputs into the next generative series. Okay. And you can see this one as a consequence of the previous one. You'll see many more, and we will be making presentations to you. The MArch students, you'll see them as their final work develops during this coming term. You will see some of the successful MSCs that have just completed last week. And we have a kind of lot of images, but we can't show you in depth today. Culture of MTech, the submission is a book. You will be, I hope, as they were, kind of blown away the first time you see them and kind of worry, can I produce that? But yes, you can. They're smiling because now they know they can do it. We pay a lot of attention to how do you describe these things, what kind of drawings, what kind of text, and particularly what kind of numerical data makes good descriptions of behavior, of morphology, material properties, and so forth. We have a lot of publications. We're very keen on publications. We're working on a new one. We hope that this year some of your work will be included in that, as will theirs. You have a call, Suhash? Okay. You get it. Okay. So we offer only 3 subjects for the dissertation, but they're enormously broad. But the dissertation proposal is a kind of negotiation. We have what we call Thesis Formation Week, which is the end of the 2nd term. During that week, you learn to write a scientific proposal. We discuss, modify. Once we accept it, that's your topic. But you're not a prisoner of it for 6 months. We expect it to develop, and there are kind of revisions. So active material systems with advanced fabrication is a kind of catch-all term. But it's really from a pavilion scale to the scale of something like this building, and it can be anywhere in there. The ecological system design, nearly all of them so far have been on shorelines and deltas, although we have had one on tundra system. So we're very keen on climate science and ecological science. We don't have any metaphors about ecology or climate, only data. So we like you to become the nerds that you dream about being. And you will be. as they have become, and they still look like normal people. Okay. And the third one, urban systems design. We started, I think, 4 years ago in urban systems. We have first PhDs by design being submitted on that, and the very first person who ever made in MTech a master's thesis on urban systems is starting next week on his PhD. So we have quite a broad body of knowledge of these systems. Urban systems for us are embedded in a culture, in a climate, and in an ecology. So all of your kind of morphogenetic processes are driven by those factors. And you will learn and you will develop skills in how to quantify and use those quantities for inputs for it. So these three guys here are doing one on the Mekong Delta, on their M-ARC, and they have studied intensively both the kind of cultural spatial models, the climate, the river flows. They're working with very advanced softwares, but they're also beginning to develop their own kind of scripts and algorithms for these processes. Okay, that's, I think, as brief as I can get it. Tomorrow, we'd like you to go and see their construction, just as next year we hope we'll be inviting a new lot to see what you have built. But we will meet you at 2 o'clock in the MTech studio on Friday, and you should have all received an email about what we want you to bring with you for that. If you haven't received it, it's 10 slides about yourself and your work and your interests, and you are allowed only 10 seconds to talk about each image. No introduction, no finish, no thank you slides, none of that kind of stuff. It's fast, it should be fun. By the end of that, not only will we have a lot of good laughs, you will all know something about each other. And work starts on Monday morning. Okay, thank you very much.